that introduction. That was generous. I can share my screen now, I think. So let's see. I will just say something if this doesn't look right, or whatever. Let's see. So here's this, and then can you all see that? Does that look okay?
Yeah, it looks good.
Okay. Okay. So thanks again, Anna, for that introduction. Thanks, everyone, for sharing your virtual lunch hour with me. So, yeah, here's a, well, I guess to start off, I'm sort of concentrating here on the theme of the whiteness of snow, right, and what makes it white. And I guess I wanted to just first put this slide out and show that like any color, which I'm sure you're all intimately familiar with, it depends on how you see it, right? It depends on what medium you're looking at it from, what sensor, what wavelength. So, for instance, this is an image of a scanning electron microscopy image of snow that's 49 days old. So pretty old and aged snow. And an electron microscope works by firing an electron beam at a substance and then looking at the return signal. And so it's not a light imaging microscope like you're probably used to using, and you can get much finer detail, and then you can also sort of see these structures that would just look sort of glaringly white in the snow, and that's what this is a picture of. And you can even see those edges there. They're grain boundaries where the snow is the sort of individual grain is bonding to the two neighbors to the left and right of it. So yeah, I'm let's see, I'm gonna minimize this a little bit so I can see it better, and move that. Okay. So yeah, my name's Ned Bair. I'm at the University of California, Santa Barbara, where I'm at the Earth Research Institute. I've posted this talk on our Box site, which should be accessible to everyone if you're interested in going back and looking at probably not any of these papers, or maybe some of the images or something like that. So that should hyperlink right there. Just copy and paste that and you should have access. Just get in touch with me. I guess I should post my email or something if it doesn't work. Okay, so a short bio to just go along with what Anna said. I after college, I went off and decided to be a ski and climbing bum, really, which was not what my parents had envisioned. But that's just an itch I've had to scratch my whole life, and haven't really figured out how to totally satisfy it. But I was a rock and alpine guide in the Cascades, so up in that upper left-hand corner, there's a picture of me guiding a group there up the summit of Mount Hood. I spent a decade ski patrolling at Mammoth Mountain, which is sort of where I really got into the snow science. That's a picture of me on the right there as a ski patroller underneath a large crown. That's an avalanche, the top of the avalanche at Scotty's. There's a picture of me skiing from 17,000 feet on Denali in Alaska. And then more recently down in the lower right is a picture of me in India doing some snow sampling. So I've sort of moved more into the research expeditions rather than the climbing and skiing ones. In 2011, I earned a Ph.D. in environmental science and management, focusing on snow avalanches. I was a postdoc at the Army Corps of Engineers. As Anna said, I've been on the research faculty at UC Santa Barbara since 2012, and I work primarily on on remote sensing. So think of spaceborne imaging, satellites, of and using those satellites to study the snow cover. Okay, so who cares about snow? Well, you should, especially, I don't know where you all are from, but I assume most of you are from the Bay Area. In California, water from the Sierra Nevada is one of California's most valuable natural resources. It sustains a diverse ecosystem, and it provides 2/3 of the water supply for the Central Valley. Where, as you may know, a large part, a quarter of the nation's food is grown. And there's some crops that are only grown in the Central Valley. Even during this interglacial period, which is now present day, right, in between ice ages, snow covers a significant portion of the Earth. And as such, almost 2 billion people worldwide depend on snow and ice melt for water. And that what comes from not just the Western US, but from places like the Indus River Basin that Anna mentioned, and I'll talk about a little later. So the snow ice albedo feedback, that's a very important part of Earth's climate. And what that is in a nutshell is, snow is very bright, which we'll talk about. And so that reflects a lot of the solar energy, that's the solar radiation that's incoming from the sun, and it keeps the surface of these snow-covered areas cool. Well, if you don't get as much snow, then you're going to have darker surfaces, because what's underneath is almost everything's darker than snow, and it's going to reflect less energy, and that's going to in turn melt more snow, and it's this feedback process, right? And it can actually go the other way, where you can have a runaway snow ice albedo feedback, which is what tends to happen in the ice ages. And that's because snow is actually a really good insulator. It's hard to melt. And so is ice. And so what can happen is, if you just get, a little bit more snow, say each year, or some, volcano eruptions, things like that are going to reflect more solar radiation, you can start building up more perennial snow throughout, year to year, and you can get this runaway effect over thousands of years, where you wind up with snowball Earth. Okay, which on the right there you have the top image is the one of the most famous images and most reproduced images in history of the blue marble from Apollo 17. The bottom is an artist rendering of what snowball Earth would look like. And the idea is that glaciers and snow and ice would cover most of Earth's surface. There's the evidence about snowball Earth is not definitive, but there is some evidence that in our past, at least glaciers and ice and snow have covered a large portion of the Earth. So the point is that making that albedo of Earth a little bit higher, reflecting a little more energy, can lead to these runaway albedo effects. Here's an image or a video actually of January through December cloud-free a cloud-free picture of Earth. And this is pretty cool because there are a lot of clouds. Earth is a cloudy planet, and it makes it difficult to see what's going on the surface, right? And so you can see that, especially in the northern hemisphere, there's a lot of snow covering the land, right? As we move, and it wanes, right, as you go into the summer. But it's covering a significant portion of the Earth, and then of course all of Antarctica. And so snow is a major part of our climate, and it's important for our water supply. Okay, what is snow? And so, as a sort of I said I'd pose these questions, right, which may be general sort of snow questions, and then I'm trying to answer them succinctly, right? And of course, the answer is always much complicated, and that's why people like myself spend their entire careers researching these things. But trying to be succinct, snow is just, it's frozen water with air, and water is H2O, right? So I'm going to see like how many of you can, or if anyone can respond here. Is that possible, Anna? I want to know.
I think people can just unmute themselves and.
Okay. Can anyone guess, in these two diagrams, the left is liquid water and the right is ice, frozen water. Which color is the H's, the hydrogens, and which color are the oxygens?
Looks like the white has to be hydrogen, right?
Yeah. Because there's two, right? Two hydrogens and there's one oxygen. And if you look at those molecules, they're all, clusters of three, right? And with the red and two whites. And then, so there's, then there's these dotted lines. And anyone want to take a guess at what those are, recalling from their high school chemistry days?
Those are the bonds?
That's right. Those are hydrogen bonds. So they're, it's in the water on the left, it's sort of disorganized looking, right? Because it's a liquid. And, those hydrogen bonds are still playing a role, but, and they cause things like, the meniscus in the test tube and capillary action and wicking and, surface tension and stuff like that. Same thing happens over with the snow on the right, except you're in a more organized structure, and snow it's a hexagonal structure, so it's six-sided. So snow flakes are always going to be six-sided. Okay, if you see a snowflake with a pentagram or something with five sides, or if you see something with a snowflake without six sides, that's wrong. Okay, they always have six sides. Now they can look different, or they can be rhymed up and have, but the base structure has six branches. That's because of the hexagonal structure. And another thing is snowflakes, they grow in the air by accretion, so they start out really tiny and they grow bigger from a condensation nuclei. So they can't have a hollow center. That's another thing that you commonly see a mistake with snowflakes. Not six-sided and a hole in the middle. Okay, so snow's it's frozen, hexagonal structure, frozen water. I'm going to talk real briefly about the electromagnetic spectrum here and how we look at snow. So here we have these really short wavelengths on the left, going all the way to really long ones on the right. Gamma rays to radios. You may know that what we see is just a very tiny portion, right, of the electromagnetic spectrum. And as the diagram shows, shorter wavelengths, higher energy, longer, lower, and then you can really see the tiny part of that spectrum that we can see in. Okay, so this is the base question, right? Why is snow white? Well, the answer is because its absorption is very low in the visible wavelengths. And I'm going to go over, this is a pretty complicated graph, and I think I'm going to try to go over it and make some sense of it for you. So, don't, I think that the theme here is that the take home is pretty easy to grasp, even though the graph looks complicated. So what we have in this graph, okay, and let me, I'm gonna try to annotate here. Okay, so these curves, the blue, the dashed green, the dot dashed red, and the black are all different types of snow with different grain sizes. So different, that picture I showed with the electron microscope, that thing in the middle, that is a grain, the round, part that's bonding with hydrogen bonds to other snowflakes. These are all different sizes, okay? And that's what you get in new snow is pretty small, that 0.05 millimeter grain size. And this is actually a grain radius, up to like a millimeter, old melting, wet snow, okay? And what you can see is that the reflectance for all these grain sizes in these shorter wavelengths. So, what are the visible wavelength range, it's around 0.45 to 0.7 or so micron. So that's a pretty, let's see if I can draw like here to here. It's a pretty small area, or a pretty small part of this graph. And you can see the snow reflectance is very high there, no matter what the grain shape is. But as you go into the longer wavelengths out here, okay, that reflectance starts to drop off, okay, in all the way, no matter what the grain size is. But it's the split between the small and the big grain sizes becomes really big, right? Like right here at this, 1.3 micron feature, for instance, okay? And you can see, this is a really wide range. And then, as you move out further into past the near infrared into the shortwave infrared, the snow reflectance gets pretty dark, especially for these large grains. I mean, it's like, some of these wavelengths, it's black because it's like zero reflectance. Okay, so we know that the snow, that's what's going on with the reflectance of the snow. Why does it get so much darker? Well, there's this thing called the absorption coefficient, and this is where the imaginary link to this lecture shows up. And I think it might be a different definition than what you're used to using. It's, if you remember from algebra, I guess, imaginary numbers, right, are if you take the square root of a negative number or something like that. Well, what we use it for here is to represent this absorption coefficient, okay? And it's part of this thing called the complex index of refraction, which describes the way that light travels through a medium, okay? And what you can see here with this absorption coefficient is that it is extremely small down here in the visible, okay? And in fact, that value right here, turns out that's actually sort of an interpolation. They had to go to Antarctica and measure snow deep in these, and its interaction with light deep in these ice core boreholes to get this, and it's probably even lower than that. The point is, it doesn't get absorbed. So that means when the light hits a snow grain, it's much more likely to bounce off and do what we call scattering rather than be absorbed when the absorption coefficient is that low. But as you can see, the absorption coefficient starts increasing, okay, as you get into longer wavelengths. And these, the absorption coefficient, these are orders of magnitude. This is a logarithmic graph, okay? These are logarithmic axes over here. So it's getting a lot more absorptive, which is why, you know, down here at these longer wavelengths, it starts to get dark, okay? And all of this is just a way to describe how snow looks at different wavelengths. So here are some other substances, you know, just so that, oh, let me turn off my annotations here. Okay, so here are some other substances, right? You know, snow, as I said, right, is you know, it's really bright in those visible wavelengths, right? And you can see this is, you know, a similar graph to what I just showed, except it's got vegetation in it, which is the green curve, and then it's got soil. And then it actually has these bands, which is from an instrument called MODIS, which shows what wavelengths MODIS, it's a satellite, a sensor on a satellite, what wavelengths it can see at. So, you know, when we're looking at snow from space, those are the wavelengths we can see. You know, we can't see, it's not what's called a hyperspectral instrument, so it can't see that entire range of wavelengths. It can only see specific ones. But you can see that the soil, right, is quite dark in the visible wavelengths, and then it actually steps up and gets brighter in, you know, the longer wavelengths. The vegetation is sort of similar, except just past the visible, okay, in the near infrared, vegetation actually gets really bright. And that's so that it doesn't overheat, and, you know, it's sort of optimized itself genetically to do that. It's actually called the red edge, that large increase. And if you mess around with near infrared photography, it's pretty cool because vegetation looks really bright there. And then you can see it sort of drops off. So, you know, this is all called spectroscopy when you're studying these curves and identifying things based on their spectral signatures, right? And which includes the visible wavelengths, but also these longer wavelengths where we can figure out what we're looking at from space. Let's see, I lost my pointer. Hold on. Jeez. That.
So Ned, I have a question that is.
Go ahead, yeah, sorry.
What's the relationship of wavelength and reflectance to heat?
So these are all, these wavelengths are pretty short. Once you go out into the much longer wavelengths, that's the thermal IR, which is where you would see, you know, like in the movies and stuff, and they show people, you know, the thermal goggles and stuff, right? Those are like looking in longer wavelengths, you know, around 10 to 40 micron.
Okay.
Now I'm going to see what I can. It's really weird. Like I still. Yeah, give me a minute to just get control back.
Yeah,
oh,
no
I see.
problem.
It thinks I'm like.
Take a moment for things to sink in. I'm sure there's a lot to understand here.
Here, I think I will be able to gain. Can I stop my share and restart it? I think,
Yeah, of course.
okay. I think it's having, okay, let me, that was weird. Boy, it really, they haven't gotten the annotation tools down very well. And I think that by now it would be pretty well established. But, okay, can you see that again?
Yeah.
Yep.
Okay. Okay, so in the longer wavelengths, you know, snow is not white. It's not that bright. It's, you know, as I showed you, it's in some of the wavelengths, you know, like 1.5 micron, and further out, it's black. What that means is that if we could see in the same wavelengths as a satellite, for instance, this is the Landsat satellite, the snow would look colorful. And what this is showing is on the left, we're looking at bands 3, 2, and 1. So red, green, blue. That's, you know, how we see and how we make up images, right? RGB. You know, compared to on the right, we have bands 5, 4, 2, which is a shortwave infrared band. That's the SWIR, which is a longer wavelength. A near infrared wavelength 4, which is sort of in between visible and the SWIR, and then green, you know, which is you know, a visible wavelength. And you can see the snow shows up as that nice sort of blue color, and the clouds show up as white because the clouds, they're still bright in those wavelengths. And so on the left, right, the clouds and the snow look identical, and they're both really bright to us. But if we could see in the longer wavelengths, we'd see that the clouds are still bright in the longer wavelengths, but they're, you know, the snow shows up darker and that nice blue, and then the land is those sort of unusual colors, and that's Mono Lake. If you're wondering where this is, and the Sierra Nevada. Okay. So back to the title of the talk, where does the white go when the snow melts? And I should acknowledge that this was a test question that my advisor used to ask his students of a alpine snowpack course. And you know, I think it's a great question, and actually pretty difficult to answer. So I've tried in one word to answer it, which is, you know, not certainly wouldn't suffice on an exam, right? It doesn't go anywhere, right? I mean, you know, the color, you know, as I said before, it depends on how you look at it and what you're looking at that object with, you know, the object's color. So, you know, for small grains, okay, and by small grains, that's usually new snow, okay? So if you look at the image on the left, that's, you know, those are your classic 6-sided, those are called dendrites, okay? And in fact, we don't really see snowflakes like that very much, especially here in the Sierra. They usually get blown apart by the wind by the time they're down, you know, at near the surface, or they also get rime on them, which are super cool droplets. So they might look more like, you know, covered, like little balls that are covered in tinier little balls. But that's what a, you know, classic snowflake looks like. That's new snow, has a very small grain size. On, you know, as the grain size gets bigger, the snow gets darker and the probability of an absorption event increases. So you can see on the right there, that's old, wet, you know, summer snow, late spring snow, and it's got these really large bonds between the grains, and all the sharp edges are gone, and that snow is just much more likely to absorb a photon and thus look darker than the small stuff, which, you know, the photons enter and bounce around and then come back at you. And that's so that's the difference. So what happens is the albedo, which is a Latin word for the whiteness, decreases. Okay, and what that graph down in the lower right hand corner is showing is that that's called the broadband albedo. So that's across all the wavelengths of the sun. it's showing that your reflectance is decreasing as you increase your grain size. And the A, B, C, D, E, those are different. They're different models and also different types of atmospheric conditions. So it depends on how high up you are. Whether it's wintertime, summertime. That it's the aerosols and the amount of diffuse light matters a lot too for the albedo. But the point is that as the grains get bigger, the reflectance decreases, which is the same thing as saying the albedo decreases. Okay, so what else happens with the white? Well, pollutants, are also something that make the snow darker, and this is a big deal because we have anthropogenic pollutants like soot is probably the biggest one, and so-called natural pollutants like dust. Although the dust dust is probably the most common pollutant in the snow worldwide, but it arises from anthropogenic or human caused things like overgrazing, deforestation, just poor land use practices. And these pollutants, they tend to stay on the snow surface. So in terms of all that solar energy coming down and messing with that delicate albedo, it's not such a big deal in the middle of the winter because you might get dirty snow. Like in fact, right now, here in Mammoth Lakes, which is where I live, the snow is kind of dirty because it hasn't snowed in a long time. But then you get some new snow on top of it, and it refreshes it with, the albedo is refreshed. It's very bright again. But in the melt season, when you're not getting that refresh, the impurities stay on the surface, and it really can speed up the melt out. So here are two pictures from a trip to India I took with a postdoc. There's me, in the lower left-hand corner, putting on some boots in a very dirty parking lot there, and that's just road grit and all kinds of junk. On the right, there's Timbo Stillinger there is in a snow pit, sort of near one of the towns. And you can see, I'm not sure if it shows up on your screens very well, but that pile of snow is quite a bit whiter than the snow around it. And that's because the snow is covered in soot from, fires. And they burn a lot of trash, and in addition to, wood and stuff like that for heating. Then there are also these dust storms that are, they're a particularly big deal in continental ranges. So like that picture is from the Senator Beck Basin in the lower right-hand corner from Mackenzie Skiles, showing what that dust compared to the, pristine snow looks like. That's because they have these point sources, off the Colorado Plateau that are to the west there that get these horrible dust storms. And I don't know, maybe some of you have been in the desert, in the Southwest desert, and seen what a dust storm looks like, and that winds up on the snowpack sometimes. So I thought I'd finish up here by just discussing some of the work that Anna mentioned that I'm doing with some colleagues on snow albedo in the Indus River Basin. This work is in review at the proceedings of the National Academies of Science. Here's another picture from that trip we took to India, in 2019. It's showing these villagers coming down from a place called Old Salong, which is up there in that terraced hillside. And they're crossing below those terraces, which is what they use for their to farm and to irrigate. It is the largest avalanche debris pile that I've ever seen. I mean, this was probably a mile or two across, and then went uphill for 2 or 3 miles maybe, and it was probably 50, 60 feet deep in some spots, and it had gouged out the earth, and there were trees and rocks. And then anyway, these villagers would walk up and down that every day as part of their, you know, going to get groceries in Salong, which is about 45 minutes away. You know, and most of those homes, you know, it's funny, most of those homes had, you know, no plumbing, were pretty open to the elements and stuff, but they had cell phones and they had satellite dishes. So, you know, pretty interesting place. So during the lockdowns, the air got dramatically cleaner in cities worldwide. You know, there were these tweets on saying things like, you know, you could see the Himalaya from Delhi for the first time in 30 years. You know, if you've ever been to Delhi, typically when you're flying in, it's kind of like going to China. You can't even see the ground on a clear day from a plane because the air is so polluted. So to be able to see the Himalaya, you know, which are the front, you know, and typically you see the snow cover because it's so bright, you know, I don't know, 100 miles away or something like that. It's pretty spectacular. Same thing with Kathmandu. So this is an article from the NASA Earth Observatory showing that the aerosol optical depth, which is really just an instantaneous measure of aerosols of you know, small particles in the air, it's showing that it's the lowest on record from compared to 2016 to 2019, right when the lockdowns began. So, you know, the hypothesis is that must have had an effect on the snowpack. And so this was from an American Geophysical Union talk where I was told that you're supposed to put the take-home points first and talk about the methods later. So I tried to do that. So that, you know, as I mentioned earlier, the Indus River Basin is, you know, supplies 300 million people with water, and it's very vulnerable in terms of these albedo and snow and ice changes because of how much of that water originates as snow and ice. So there you can see, you know, Islamabad, New Delhi, and the Indus, and what that image is showing is some modeling results showing the decrease in melt that we found from having a cleaner snow and ice cover during the lockdowns in 2020 compared to the past 20 years, because MODIS has a pretty long record length now. So we actually found that the snow and ice was cleaner by about 30%, okay, which is, that's 22 parts per million by weight equivalent dust, okay? And the reason why I say equivalent dust is because the pollutants are typically dust and black carbon. We can't tell the difference with the satellites, so we can use the dust as a proxy, you know, assuming that it's the most prevalent pollutant. Anyway, it changed the timing of about 6.6 cubic kilometers of water. So in other words, 6.6 cubic kilometers of water didn't melt in the 2020 water year. Okay, a water year goes from October 1st through September 30th. So, you know, for comparison, the largest reservoir in California is Lake Shasta, and it holds about 5.6 cubic kilometers of water. And if you've ever been up to Lake Shasta, that's a big reservoir. You know, it's not one of the biggest reservoirs in the country, but it's the largest in California, and it's a large reservoir. So it's a lot of water that was affected, we think, by the lockdowns. You know, just briefly on the methods. So we looked at snow cover, as I said, over the past 20 years. We used two models. Both of the models assume mixtures where the observed is composed of a specific type of snow and a snow-free component. So what we can do is we can look at the pixels, you know, how to describe a pixel. It's like you know, in an image, the little blocks. You know, it's got some intrinsic resolution. Like these pixels are pretty big. They're about 0.5 kilometer each. we can look at the background there, and that's what that's the spectra. So the albedo, the spectral albedo at each of the wavelengths, that's what it actually looks like from the satellite in red when there's no snow on the ground. Then when there's snow on the ground, we get the observed. So we have the blue, okay? And then the black is we can fit a model to that and guess what type of snow is on the ground. You know, grain size and impurity content. So both models showed that 2020 dust levels were significantly below the mean and near the lowest levels recorded over the past 20 years. You know, on the left is, you can see, we're only looking at that melt period, as I said, because of the fact that the snow, right, gets refreshed and that albedo gets refreshed throughout the winter. And then also in this part of the world, beginning in July is the monsoon. Okay, and the monsoon, you can't see much. It's pretty cloudy, especially as you move to the south and to the east in the Indus. But you can see that red line, even accounting for uncertainty, is quite a bit below the mean in both models. You know, and the models have differences in terms of you know, how much dust they estimate and all that, but the trends are the same. Show that, you know, they both show that 2020 was, you know, one of the cleanest and at sometimes the cleanest snowpack, snow and ice cover on record. You know, just because I'm a scientist and you always have to report caveats, right? Snow albedo, it depends on the impurities, but it also depends on that grain size stuff, as I was talking about earlier. You know, there's more uncertainty in the grain size retrievals because those wavelengths are darker and because of remote sensing issues like things called atmospheric windows and what wavelengths you can see it and stuff like that. There's a little bit too much uncertainty to say that 2020 was brighter overall than the other years in terms of the snowpack, but there's some signs of that. So for instance, this is with the first model. You can see that right at the end towards July, at the end of June, that red curve no longer intersects the black. And what you're looking for is that have that red curve be above the black to be able to say definitively that, you know, it was brighter in 2020. That's it. These are the works cited. There's a picture of our Jeep with a snorkel and manual transmission, no power steering on that. You know, drive was on the right-hand side, and yeah, driving that thing around in the Himalaya was interesting, but beautiful spot. And I think, let's see, do we have time for questions?
Yeah, for sure. I was going to
Okay.
say, if people have questions, you can either put them in the chat and then you can answer them, or if you want to unmute yourselves and ask away. Yeah, we probably have about, like, I don't know, 10 minutes or so. Thank you so much. That was extremely informative and complex, and there must be questions.
I have a question. Thanks for doing this. It's really interesting. I'm wondering, it's interesting to hear you talk about the new and the old snow. And I'm wondering if you can talk a little bit about if snow aging is a product of time, or if it's like a heat and, you know, temperature, pollution, weather kind of experience.
Yeah, so that's a really interesting question. So my old colleague on Mammoth Patrol, Walter Rosenthal, used to say snow is hot. And what he meant by that is that its homologous temperature is really high. And what the homologous temperature is it's the temperature of the substance divided by its melting temperature. And if you think about it, all snow on Earth exists pretty close to its melting temperature. I mean, like, you know, here in the Sierra right now, it's snowing, and it's probably the temp, you know, it's not always the snow can be a little bit colder than the air temperature, but it's, it's probably like 28 degrees or something like that. And it's, melting temperature is 32. So, that homologous temperature is really high. So what that means is there's a lot of mobility for the atoms. And we get this in like, powdered metallurgy, blacksmithing, you heat up metals, right, to work with them. Well, same thing with the snow. So the snow, as soon as it falls in most places on Earth, it just starts changing really rapidly. And it starts reducing its surface area specifically. Okay, so you get less jagged and more rounded. And a lot of those are they're curvature effects. Okay, that's why it does that. Also, snow. I had a question about this the other day. Like right now, we're getting it hadn't snowed in a month here really, and you're seeing all these raised ski tracks and stuff like that, and people are calling it age hardening. And it's like, well, it's not the same as age hardening for the way that you would define it for metals, where you apply heat and harden and strengthen the steel in a very specific way. But what's happening is that snow is more compacted than the snow around it. So it's going to be stronger because it's more compacted and denser, and all the other stuff blows away. And so what you wind up with is these footprints, whatever, where someone's traveled and they're raised above the snow. So I don't know if that answers everything, but okay.
What's the net effect heat-wise if we had something like 2020 happen for multiple years? What's the net effect heat-wise in the atmosphere?
Yeah, I mean, that's a good question. So first of all, this is I was only looking at the Indus, and one of the reasons why is because it's so polluted there. And with these satellite sensors like MODIS that I was talking about, it's a pretty, it's sort of a meat cleaver versus a scalpel for the detecting the impurities. If it's really dirty, you could tell that. But small, like for instance, there's no clean snow doesn't really exist in the world, except maybe in parts of Antarctica. Like even in the Arctic, if you go up there and sample snow in the middle of nowhere, you'll find small amounts of black carbon from, cars and people burning stuff. You can't detect that with MODIS. It's just the signal's too low. But that said, there's cities and worldwide, there's been there's more research that's starting to come out. These science questions, right? They don't get answered immediately, and I think you'll see more of this over the next year. We saw pretty dramatic reductions worldwide in atmospheric pollutants, and so it's actually a really complicated effect because okay, so the snow gets cleaner. That means that it's going to, it's going to be brighter. It's going to reflect more solar energy. Well, conversely, though, and I mentioned this, if you have a lot of aerosols, those aerosols themselves actually reflect solar energy too. So there's actually less energy that's making it to the snow surface when you've got a cleaner atmosphere. We see this with volcanic eruptions, right? And maybe what killed the dinosaurs, meteorite impacts and stuff. You get a lot of dust in the atmosphere and stuff. You get cooling actually. So that's where something called it's not just about the albedo, it's the forcing, which takes into account how much irradiance, how much solar radiation there is. So these effects are really complicated. And yeah, I don't have a good answer in terms of how global climate would be impacted by a cleaner snowpack. But I guess the point that I would like to sort of try to hit home is that our our climate is delicate, and we're doing things that we can see, have an effect on, like a pretty big effect on our water supply, and the COVID-19 lockdowns have made that really salient.
I have a question. Is the snow only reflective when it's, or like more reflective when it's fallen on the ground and is like in one big mass, or does it also have like a reflective quality when it's still, I mean, I guess, is it snow when it's in the cloud? Like before the snow falls, is it considered snow? Like at what point is it snow versus the thing before snow? And
Yeah.
it's reflective also.
Yep. Yeah. So it forms just like rain, where it basically gets heavy enough to fall out of the sky.
Yeah.
So yeah, it is snow when it's falling. And when you look at a weather radar, for instance, and you see typically it depends on the color scheme, but like, for the Bay Area or something, they'll have like green as rain, and then you'll have like the mixed kind of area, the dreaded wintry mix, which is sort of like, pink, and then the snow will be, white. And that's snow in the air that the radar is bouncing off of, and they can come up with those color schemes because the radar reflectivity is very different. So yeah, of course, snow in the atmosphere is, falling snow is very important too. It causes whiteouts and all of that. What my work tends to focus on, right, is the snow on the ground, because that's what melts and runs off and either becomes, goes into the groundwater or goes into streams or whatever. But yeah, it forms in the atmosphere just like rain.
Can I ask one more question really quick?
Sure.
Are there other frozen substances that aren't frozen water that we have on Earth that are also reflective? Like other planets have like frozen methane and stuff. Do we have other frozen things that are reflective here?
Not as reflective as snow. Typically, a lot of that stuff you have to have really cold temperatures, and there are actually different kinds of ice throughout the universe. Most of them don't exist on Earth because it's not cold enough, or the pressures need to be too high. But yeah, you can have that ice 1H is what I showed you, the hexagonal structure. There are also other crystalline structures of ice, but we don't see them on Earth, at least not very often.
I have a question. I guess it's maybe more of like a clarification something that I feel like I need to understand, which is about the absorption coefficient. Okay, so that is when we were talking prior to you doing, and like talking about you doing this, and you were like, yeah, snow is an imaginary number. That's what you're talking about? Is that like the absorption coefficient is an imaginary number?
Yes. So
Okay.
I think so. The that absorption coefficient K, the sort of magenta curve.
Yeah.
What that is that yes, there's a complex refractive index of ice, okay, that has a real, and an imaginary component to it, okay, and that complex that absorption coefficient is the imaginary component.
Okay. Got
it. And they all together they describe how light interacts with the medium and how it bends, Snell's law, how it refracts, and yeah.
Okay, cool. Yeah, thank you. I think Calvin, did you have a question?
Yeah, thank you. Thank you so much for this talk. First and foremost, I just had a question of whether or not there is also a measured effect between snow's reflectivity and photosynthesis in evergreen plants.
Like, are you asking if you can, I'm not sure I would, what immediately comes to mind is that you can have photosynthesis under the snowpack. For instance, late in the spring, when the snow gets what's called optically thin, meaning that you are seeing some of the underlying surface underneath it if you were to look at it. So you might see that on, with thin snow or even ice, you can sometimes, if it's on asphalt or something like that, it looks dark underneath. Well, that's because you're seeing probably the asphalt. What you can have is actually, you can have plants, and it's easiest to see with like grass or something, but you can see it with, manzanita or whatever. There's enough solar energy making it through the snowpack that's being, what's called transmitted by the snowpack. So it just goes through it, doesn't bounce out, doesn't get absorbed, doesn't, bounce out back towards the sun, that photosynthesis can occur. But I think you were asking something else maybe, which I didn't quite get.
No, well, also in the light reflected back from the snow, like back towards the undersides of plants that are breaking the surface of the snow.
Oh, okay, yeah. So that's, we usually talk about multiple reflections for that kind of thing, and it is, that is, sort of an issue with remote sensing, and when you're trying to figure out, why is the signal so bright and stuff like that in the mountains, because if you have, a real steep terrain, they're both snow covered, you can get a really strong reflectance back actually above 1. But in terms of, it's all diffuse. So it's not it's not nearly as strong as the beam of the sun. Okay, so like so it, I imagine it has some effect because like I know some plants don't like direct sunlight and they do better with diffuse light. So I guess it's not something I thought of, but I guess for that type of sort of shade tolerant plant, the snow would provide enough light for photosynthesis.
Thank you.
We probably have time for about one more question if anyone has something out there. Looks like we have another question from Kylie White in the chat. She says, what is your definition of imaginary in this context?
Yeah, I mean, boy, I think I just to go back, I would probably say the imaginary number and that absorption coefficient and that description of snow being, being very transparent, not absorbing anything in the visible, and then increasing, orders of magnitude, in the longer wavelengths.
Yeah, that's very interesting. Thank you. Well, this has been so interesting and helpful. I'm so glad everyone who's out there came. And Ned, thank you so much for taking the time to, to share your knowledge about this stuff. Yeah, it's super helpful. Yeah, I guess this is it. Make
What?
sure and stay tuned if you want to come to any more of these. I think your buddy Martin Schneebeli is gonna come on next time and talk about the microstructure of snow and how I think like how crystals are oriented in the snowpack, I think, stuff like that. So yeah, and then we'll have Kylie White later on and I having a conversation about mythos and the horizon and I think a few others. So anyway, thank you so much for coming and being a part of this project.
Okay, yeah, thanks everyone. That's awesome. Martin, he'll be great, and I think have some really interesting stuff with his microtomography, and I appreciate the good questions, and I hope this is useful to you in an artistic sense and not too technical. I don't know.
Yeah, no, it's great. I think it was really, really helpful. Thank you so much.
Okay.
Thanks, everyone.